Last time you swung a door open in my face and walked off. You'd spent 2 whole nights convincing me the world is made of things that rock. Out and back, around some resting spot. The swing, the string, the trembling atom. And then, right at the door, you looked up and said, "But the other great motion isn't the rocking at all, it's the round and round. The moon wheeling around the earth, a planet wheeling around the sun, each one held on its curving path by a single, reaching force. And you told me my old energy landscape would come walking in tonight, bent into a stranger shape, doing a job I'd never guess it could. You said its name was the orbit. So here I am. Pay up."
I mean to pay in full. But give me your mood first. You never walk in without one.
My mood is a question I've carried since I was a small child, and nobody ever answered it to my face. If gravity is forever hauling the moon down toward the Earth, never resting, pulling on it every second of every night, then why in the world doesn't the moon just fall down and crash into us? Why does it hang up there, going round and round, when everything else gravity touches drops? An apple falls off a tree. The moon doesn't. What's the moon got that the apple hasn't?
That is the oldest question in the sky, and it has an answer that turns your stomach over in the good way. But it needs 2 ideas standing together. Neither one alone will do it. So let me name tonight's 2 before we take a step. The first is a quantity, a going-around quantity, one you and I have already met and walked away from. The second is a shape, a landscape, the very one you drew on the energy night, come back wearing a disguise.
A going-around quantity. Now wait, 3 nights ago, on the momentum evening, you dangled exactly that in front of me, and then snatched it back. You said a going-around quantity was a cousin, a different conserved thing, kept in its own ledger, saved for a later night. You practically wagged a finger at me not to let it blur in with the rest. And now you're telling me tonight's the night the cousin shows up.
Tonight, the cousin sits down at the table. It has a name, angular momentum, and it turns out to be the hinge the whole orbit swings on. So there's the shape of the evening laid out, a certain kind of force, the cousin that force keeps safe, and a landscape that answers the question you've carried since you were small. And we start with the force, because everything hangs off what kind of pull gravity really is. So tell me, what's so special about the way gravity pulls?
I'll bite, though I suspect I'll get it thin. It pulls things down, it's strong, it never quits, it reaches everything. That's about as far as my everyday picture goes. A great invisible hand always pressing down.
There are 2 things worth pinning underneath that, and I want you holding both. The first, which way does it point? Straight at the center. The Earth pulls the moon dead along the line joining them, aimed right at the Earth's middle. The sun pulls a planet straight at the sun, always toward the center, never off to one side. A force built that way has a name, a central force, aimed forever at one central point and nowhere else.
Always toward the center, fine. And the second thing?
How strong the pull is depends on one thing only: how far away you are. Not which direction you've wandered off to, not how fast you're moving, just your bare distance from the center. And it fades in a particular steep way as you back off. Go twice as far, and the pull isn't half of what it was. It's a quarter. Back off to 3 times the distance, and it's a 1/9. It weakens with the square of the distance. That's the inverse square, and it's the fingerprint gravity leaves on everything it touches.
Twice as far, a quarter the pull. That drops off faster than I'd have thought. I'd have guessed something gentler, a slow easing. So gravity's got a long reach, but it thins out quick the moment you pull away. Close in, it's fierce, and out far, it's a whisper.
A long reach that thins out fast. Now, before we get to the moon, you already know a central force in your own hand. Have you ever swung a stone on the end of a string, round and round over your head?
As a kid, endlessly. Whirl it round faster and faster till the string's near horizontal and singing, and you can feel it straining to get away from you.
Good. Hold on to that straining. We'll come back to it. So while it's whirling, which way is the string pulling the stone?
Straight in, toward my hand, along the string. Whatever else is going on, the string is hauling the stone in toward the middle the whole time. It's got no other direction it can pull. It runs from my fist to the stone, so it pulls along itself.
A central force, in your fist, always aimed at the center. Now here's the thing to sit with, because it's the whole puzzle in miniature. If the string is only ever pulling the stone inward, toward your hand, why doesn't the stone just fall straight in to your hand? Why does it stay out there, going round and round instead?
Because it's moving. It's rushing sideways, round the circle, fast. The string keeps yanking it inward, but the stone keeps shooting past sideways before it can arrive, so it never reaches my hand. It just curves around me instead of dropping in. The inward pull bends its path into a circle rather than reeling it home.
Now let go of the string. What does the stone do?
It flies off. And here's the part I remember surprising me as a kid. It doesn't fly straight outward, away from me, the way you'd half expect. It shoots off sideways, in a straight line, whatever direction it happened to be heading at the instant I let go. Off across the yard, dead straight.
Which tells you something you'll badly want later tonight. Nothing was ever flinging that stone outward. Not really. The only pull in the whole business was the string hauling inward. The stone's own sideways rush did all the rest. Cut the inward pull, and it doesn't rush out. It sails off straight ahead, along the last direction it was going. That felt outward strain on your hand was just the string fighting to bend the stone's stubborn straight-line rush into a curve.
Inward pull plus sideways speed, and the curve is what you get from the two together. And, oh, that's the moon, isn't it? Gravity's the string. There's just no string. The Earth's reaching in on the moon like my fist on the stone, and the moon's rushing sideways too fast to fall in.
There's just no string. And now here's the turn on your childhood question. You asked why the moon doesn't fall. The answer starts by agreeing with the part you were sure was wrong. The moon is falling. Right now. This instant. And every instant. Without pause.
Falling? The moon is falling. No, that can't be right. It's not getting any closer to us. It's been up there at the same distance my entire life, and my grandmother's before me. If it were falling, it would have landed on somebody's roof by now. Things that fall arrive.
Both are true at once, and holding them together is the whole trick of the night. Picture yourself on top of a mountain, an impossibly tall one, poking clear up above the air, and you've hauled a cannon up there with you. You fire it flat, dead level, straight out over the edge, out over the world. What does the cannonball do?
It flies out fast, and then it curves down and thumps into the ground some way off. Same as anything thrown. A ball, a stone, an arrow. It arcs. And the harder I fire it, the farther out it gets before gravity wins and drops it into the dirt.
Just so. Fire it harder. It flies farther before it hits. Harder still. Farther yet, out past the next valley. Now hold one more thing in mind at the very same time. The thing that changes everything. The Earth is round. It's a ball. So as your cannonball flies way out past the horizon, the ground underneath it isn't staying flat and level.
Right, the ground is curving away, bending down and dropping off under it because the whole planet is falling away into a curve beneath the ball's path.
So now fire the cannon so ferociously hard that as the ball drops toward the ground curves away beneath it just as fast as the ball falls. The ball keeps dropping, and the Earth keeps bending out from under it, and the two rates match.
Then the gap between them never quite closes. The ball is falling the whole time, plunging toward the Earth, but the Earth keeps running away downhill from it at the same pace. So it never gets any nearer the ground. It falls, and the ground ducks. Falls, and the ground ducks.
The gap never closes. The ball falls and falls and falls, always pulled down, always dropping toward the center. But it's rushing sideways so fast that the round earth curves away beneath it as fast as it drops, and it misses the earth completely, the whole way around, and comes back and clips you in the back of the head.
Oh, so the going round isn't the opposite of falling at all. The going round is falling. It's falling and forever missing the ground because it's moving sideways too fast to ever catch up with it and land. The moon isn't refusing to fall. It's falling as hard as the apple. It's just missing.
Falling and missing. The moon is doing just what your cannonball does, pulled straight down every instant, dropping toward the earth forever, but flung sideways so long ago that the earth curves away beneath it and it never arrives. Nothing holds it up, no shelf, no string, no hand. It just keeps missing.
So, a cannonball fired hard enough that it can never come down? Fine, but then nothing holds it up at all. It's just plummeting past a planet that keeps sliding out from under it. That's really all there is to it.
The moon is a very fast apple. The same gravity that drops the apple off the branch pulls on the moon in the very same way. And that was the leap Newton made, to say those aren't two forces, one earthly and one heavenly, but a single gravity reaching all the way from the orchard to the sky. The apple falls a few feet and lands. The moon falls too, just as surely. But it was flung sideways once, so fast, that it's been falling and missing ever since.
And very fast. How fast are we talking? Give me a feel for it since you won't hand me a number.
Faster than any rifle shot. Faster than the crack of sound. A blistering sideways rush. And it costs nothing to keep up. The moon was flung once, long ago, and it's been coasting on that single hurl ever since. No engine, no fuel, no effort. That blistering sideways speed is the whole reason the earth curves away beneath it before it can ever fall to the ground.
Let me test the edges of it because it still feels slippery. What if I don't fire the cannon hard enough? Too little sideways speed?
Then it's just a long throw. The ball drops faster than the ground can curve away, catches up with the earth and lands. A big arc out and down, same as a stone flung from a sling. Too slow, and you fall and hit the ground like everything else. There's one particular sideways speed where the falling and the curving away finally match, and that's the one that never lands. It falls in a circle forever instead.
And if I overdo it? Far even harder than that round forever speed?
Then it swings out wider than a circle before it comes arcing back, riding out far, slowing and returning, tracing a longer stretched loop. Harder still, and past a certain speed, it never comes back at all. It climbs away and leaves for good. Hold all that lightly for now. We'll draw it properly later tonight with the landscape. For the moment, too slow you land. Just right, you fall forever in a loop. Too fast, you're gone.
All right, falling and missing. I've got it. And I genuinely like it. It's the first time that question's ever had a real answer instead of a shrug. But you said it takes two ideas, and that was only the force. Where's this cousin, the going around quantity? Bring it out into the light.
It steps right out of what a central force is, so we've already half built it. Think about it with me. A central force points always straight at the center, straight in along the line. Now a pull aimed straight inward can speed the moon up as it drops toward the center, or slow it down as it climbs away. That much it can do. But there's one thing such a pull can never, ever do.
Go on. What can't it do?
It can never give the moon a sideways shove, a twist around the center, because it never once points sideways. It only ever points dead in. It's got no sideways component to push with, any more than your string could shove the stone along its circle rather than toward your hand.
Right. If the force runs purely along the line to the center, then none of it points around the center. There's no part of it doing any twisting, any spinning up or spinning down of the going around. It can pull the moon in and let it climb out, but it can't touch how the moon wheels.
And so the amount of going around the moon carries, its wheeling about the center, cannot be changed by gravity, because gravity has no sideways hand to change it with. That going around holds dead fixed for all time. And there it is, the cousin from the momentum night. Angular momentum, the quantity of going around. A central force keeps it locked, because a central force has no twist to spend on it.
So it's the same shape of argument I've seen twice from you now, a quantity the force simply can't get at, so it never changes. Energy was one of those. The force couldn't touch the total. Momentum was another. And this going around is a third, locked for the same kind of reason. The force has no way to reach it. You keep finding these untouchable numbers.
The same shape, a third time. And unlike the other two, this one wears a face you can see drawn right across the sky. Let me draw it for you. Take the line running from the sun out to the planet, a long, taut string joining the two, and watch it as the planet travels along its orbit, like a single hand sweeping around the face of a clock. As it sweeps, that line fans out a thin slice of the orbit's inside, hour by hour, covering area. And the locked going around forces one thing to be true about those slices. The line sweeps out equal area in equal time. The going around quantity is essentially how fast that sun-planet line sweeps out area, so locking the one locks the other. Equal areas is just the going around made visible. Every hour, the very same size slice of area. Always the same, all the way round the loop.
Equal slices in equal times. Let me say what I think that means for the planet because it seems plain enough. If the line's sweeping out the same amount of area every hour, steady as a metronome, then the planet itself must be cruising round the loop at one even, unchanging speed. Same pace the whole way round the track. That has to be it. Steady area, steady planet.
That's the sensible reading, and it's wrong. Think about the shape of that sweeping line. When the planet is far out from the sun, the line joining them is long. When the planet swings in close, the line is short. Now, to fan out the same size slice of area in 1 hour, first with a long line and then with a short one. Which one has to swing around through a bigger angle? Which has to hurry?
The short one, surely. If my line's short, I've got to swing it through a big, fat, wide angle to sweep out a slice the same size. So when the planet's in close, it has to be whipping around fast. And when it's far out, with that long line, the tiniest lazy drift already sweeps a fat slice. So out there it barely has to move. It's crawling. So it's not steady at all. It's fast when it's near and slow when it's far. My even cruise is plain wrong.
Wrong. And now you see why. Picture the two slices side by side. Near the sun, the slice is a short, fat, stubby wedge. Far out, it's a long, thin, skinny splinter of a thing. Same area, but wildly different shapes. To lay down that stubby, fat wedge in an hour, the planet has to swing through a big angle quickly. To lay down the long, skinny splinter, it barely stirs.
So near is fast, and far is slow, and it's forced. The planet has no choice if the areas have to come out equal every hour. It's not cruising a track, it's plunging in, whipping hard around the sun, and coasting slowly back out. Racing where it's close, loafing where it's far.
Racing near, dawdling far. A comet is the great showpiece of it. It comes tearing in around the sun over a matter of days, whips around hard and close and bright, then goes crawling back out to spend a whole human lifetime creeping through the far, cold dark before it ever returns. And mind, that speeding up and slowing down isn't the planet gaining or losing its going around. The going around is fixed. It's only trading how that same fixed amount gets spent. Out far, spread wide and lazy across a long line, in close, crammed into a tight, furious little whirl.
Which sounds a lot like something I've felt in my own body, now you put it that way.
It lands on a picture you carry in your own body, though I'll hand it to you carefully because it's a cousin of tonight's idea, not the identical twin. The figure skater, spinning on the ice, arms flung out wide, and she turns slowly. Then she snaps her arms in tight against her chest, and suddenly she's whirling fast enough to blur.
Arms in, and she speeds up all on her own, without a push. That's the same going around held fixed, isn't it? Pull in, spin faster.
The same conservation, and no other. But here's the difference I don't want you to swallow whole. The skater is spinning about her own middle. That's spin, a body turning on itself. Our planet isn't spinning on itself, it's wheeling around a far-off center, the sun, way out there across empty space. So take the skater as an analogy. The same law, the going around held fixed, so drawing in means speeding up. But not the same situation. The planet pulling in close to the sun and racing is like the skater pulling her arms in and racing. A rhyme, not the same word.
Got it. And I'll keep them apart. The skater spins on herself, the planet wheels around something far off. Different setups, but both obey the one rule: draw in, speed up. It's an echo, and I shouldn't weld the two into one thing and pretend they're identical.
Cleanly held. And there's an even plainer version waiting in your kitchen sink. Water circling the drain speeds up into a tight, fast whirl as it draws in toward the middle, while it drifts slow and wide out at the rim. Draw in, quicken. Spread out, slacken. One law wearing two coats. So now you're holding both of tonight's stars at once. The force is central and inverse square. The going around it keeps locked is angular momentum, and its visible face in the sky is this racing near, dawdling far.
Both in hand. So now, bring me the thing you promised would answer the whole childhood question. The landscape, bent.
For that, I need the energy knight back in the room. Let me remind you what that landscape did, so it's fresh in your hands. 2 nights ago, I drew a curve, position running along the bottom, and the shape rising into hills and dipping into valleys. And the moving thing behaved as if it were a ball rolling on that very shape. Quick down in the valleys, slow up on the hills. Then I laid one flat level line clear across it, the total energy, the number that never changes, and you read the entire motion straight off the drawing.
I remember it cold. Down in a valley, below the peaks, the thing's trapped. It rocks back and forth between 2 turning points, the spots where the flat line meets the curve, and the speed dies to nothing. And if the line clears a hilltop, there's no turning point on that side, so the thing crests the hill, still moving, and escapes for good. Bound in the valley, or free over the hill. But how on earth does an orbit become a ball rolling on one of those curves? My orbit's a thing looping around in the flat of the sky. It's not going up and down a line, it's going around. Those are 2 completely different motions.
That's the knot. And here's how we untie it. And it's the going around quantity itself that makes it legal to do. You're quite right. The orbit lives in a plane, spread out flat, with 2 whole dimensions of room to move in. That's too much to squash onto one simple hill and valley drawing. So we do something clever with the going around. We fold it away. Because the going around is locked, the whirl is no longer free to be anything it likes. Once you fix the radius, the whirl is fixed along with it. So the radius carries all the freedom that's left. And that's what makes it legal to watch the radius alone. We stop tracking the whole 2-dimensional loop, and we watch a single number instead, the radius. Just how far the planet sits from the sun, and nothing else. Not where it's got to around the loop, only how far out it is at each moment.
Only the distance. In and out, near and far. One number on a dial, rising and falling as the planet swings close and swings wide. I throw away the going around part and just watch that dial breathe.
And here's what folding it away buys us. That one number, the radius, obeys a landscape, a real hill and valley curve, the same ball on a shape from 2 nights ago. The planet's distance from the sun rolls in a valley like a ball on a hillside, and once you've got the valley drawn, you can read the whole orbit of it with your eyes. And I get to tell you what that valley is built out of, because it's built from 2 pieces added together.
2 pieces. Give me the first.
The first is just gravity, the real pull, drawn as a landscape the way we drew the Earth's gravity on the energy night. It's a well, a slope running downhill as you go inward. The closer you creep toward the sun, the deeper down the slope you slide, because the pull grows fiercer the closer you are. On its own, that piece is nothing but a pit, a slope that only ever drags you inward, down toward the center.
And if that were the whole story, the planet just slides down the pit and smashes into the sun. Which is my childhood question all over again, only now you've drawn it as a picture. A pit, and a thing helplessly sliding to the bottom of it. So there had better be a second piece, or the moon's already dead.
The second piece is the one that saves it, and it comes straight out of that going around we folded away. Folding it didn't make it vanish, it left a mark on the landscape. It throws up a wall, a steep wall, rising on the near side at small radius, right where the planet would want to slide in toward the center.
A wall, rising up out of nothing, right where the planet's trying to go. Where does a wall come from?
From the going around, refusing to be squeezed down to nothing. Remember the equal areas. The closer the planet comes to the center, the more furiously it has to whirl around. And a fast whirl carries a great deal of sideways motion energy. Squeeze the planet further in, and it must whirl faster still, which costs more and more energy. And that rising energy cost, drawn as height on the landscape, is the wall itself. Try to drive it right down onto the center, and it would have to whirl impossibly, endlessly fast, which it simply cannot do. So the going around fights being crushed inward, and in this flattened radial picture, that fight shows up as a steep wall barring the way in. It has a name, the centrifugal barrier.
A wall on the inside. So gravity's a slope pulling the planet inward, and this barrier is a wall shoving it back out, right near the center. They're set against each other.
Now I have to flag one thing with care, because it's a famous trap. That barrier is not a real push. The only true force in the whole story is gravity, pulling inward. The barrier is the going around in disguise, wearing the costume of an outward push once we've squashed the picture down to the radius alone. The full story of these costume forces is a whole night of its own. For tonight, it behaves like a wall, and that's all we need.
Noted, and I'll hold it apart carefully. It's not a real outward push, it's the going around in disguise, wearing the mask of a force because we squashed the picture flat. And there's a later night that comes clean about the disguise. All right, now put the 2 pieces together for me and let's see the shape.
Add them. The inward gravity slope, running downhill toward the center, plus the outward barrier wall, rising up steep right near the center. Picture a long slope coming down from far out on the one side, and a steep wall climbing up from the inside on the other. What single shape do you get when you add a slope going down and a wall coming up to meet it?
They've got to meet somewhere in the middle and turn the corner. The slope comes down from far out, the wall comes up from close in, and where they meet, there's a low spot between them. That makes a dip, a trough, a low floor with the wall on its inner side and the long slope on its outer side. It makes a valley.
A valley. There it is, straight out of the 2 pieces. The centrifugal wall making its steep inner side, gravity's long pull making its gentle outer side, and a low floor sitting between them. And now, every last thing you learned on the energy night comes flooding back, because this is that same landscape, and you already know how to read it. So read it. Lay a flat total energy line across this valley, and tell me what the planet's radius does. Start with the line laid right along the very floor.
Let me do it just the way I did 2 nights ago. If I set the planet right at the very bottom of the valley, the lowest point, where the ground's dead flat, then it just sits there. There's no slope to push it either way, so the radius never changes at all. And a radius that never changes means the planet stays at one fixed distance from the Sun the whole way around the loop. That's a circle. A clean circular orbit sits right at the bottom of the valley.
The bottom of the valley is a circle. The radius pinned at one value, never budging, the planet holding one steady distance forever. Now lift the line a little, up off the floor, and give it some room to move.
Lift it a touch above the floor, and now there's a gap between my flat line and the curve. So the radius isn't stuck anymore. It can roll. It rolls down to the floor, up the far side, to a turning point, where the line meets the curve, stops, comes back down through the floor, up the near side to the other turning point, stops, and back again. It rods. The radius rocks in and out, between a nearest distance and a farthest one, over and over, without end.
The radius breathes. In and out, once every lap around the Sun, closest at the bottom of its swing, farthest at the top of it, and a distance that swings between a near value and a far value, once per trip around the loop, is no longer a circle at all.
It's an ellipse. That breathing radius drawn out in space is a planet on an ellipse, sweeping in near the Sun and back out far, near and far, lap after lap. So the circle was the ball sitting dead still on the valley floor, and the ellipse is the very same ball rocking in the very same valley. I did not see that coming, that the ellipse is just the rocking version of the circle. Same bowl, one's resting and the other's sloshing.
Same valley, only a different amount of rock in it. Sit dead still at the bottom, a circle. Rock it gently, a near circle, a soft little ellipse, barely stretched. Rock it harder, a wider swing between near and far, and the ellipse pulls longer and more drawn out until it's a real cigar of an orbit, plunging in tight past the Sun and swinging way out into the dark. And now finish the reading for me. Pour in enough energy that the flat line rises clear above the outer rim of the valley, the very top of gravity's long outward slope. What happens then?
Then it's the escape case, the same one as the rocket clearing the hill from the energy night. The radius rolls outward, up the long outer slope, and if my line's sitting above the rim, there's no turning point out there for it to meet. The gap never closes. So the planet just keeps rolling outward and never comes back. It climbs clean out of the valley and coasts away into the dark forever, a thing that swings in past the Sun once and then leaves and never returns.
An unbound flyby. It falls in toward the Sun, whips around it a single time, and sails off never to come back, riding right over the rim of the valley. And mind the shape of that rim. Gravity's outer slope rises and then levels off toward a ceiling. It never crests into a hilltop with a downhill on the far side, so clearing the rim means rising past that ceiling, not going over a hump. So look at what a single valley has just handed you. Sit at the bottom, a circle. Rock in it, an ellipse. Clear the rim, an escape. The circle, the ellipse, and the flyby, every shape and orbit is allowed to take in the whole sky, are one ball rolling in one valley, read straight off the landscape, the same as 2 nights back.
And hold on, let me go back and collect my childhood question, because I think you've just answered it and I want to be the one to say it out loud. The moon doesn't fall down into the earth because the barrier's in the way. The going around throws up that inner wall, and the moon simply can't get past it, down to the center. And it doesn't fly off into space either, because gravity's outer slope holds it in. It hasn't the energy to climb the rim. So it's caught between the wall and the slope, trapped down in the valley, and it does the only thing there is left to do down there. It rocks. It falls in toward the earth, The wall turns it back out. Gravity hauls it back in. The wall turns it out again. Over and over, forever. It's just a ball rocking in a valley. That's the whole of the orbit.
You've answered the oldest question in the sky in your own words. The moon doesn't fall in because the barrier holds it out. It doesn't fly away because the well holds it in. It's trapped in the valley between the two, and it rocks there, falling and missing for as long as the valley stands.
And those two ends of the rock, the closest point and the farthest point, those are the planets truly nearest and farthest from the Sun on the whole loop.
The closest point and the farthest point of the entire orbit, the very bottom of the radius's swing and the very top of it. The planet comes nearest the Sun once a lap and swings farthest once a lap, and every moment in between it's simply on its way from the one to the other, racing as it closes in, dawdling as it draws away. Two special points on every ellipse, red straight off the rock of the valley.
Then let me get greedy and ask what sets which one I get. Circle, gentle ellipse, long cigar, escape. What's the dial I'm turning to slide between them?
There are two dials, and you've had your hands on both already tonight. The first is how high you lay that flat line across the valley, which is just the energy. Right down on the floor, a circle. A little above, a gentle ellipse. Higher still, a long stretched cigar. Up over the rim, escape. More energy, more rock, a wider orbit.
And the second dial?
The going around itself, how much of it the planet carries. That's what sets the shape of the valley in the first place, before you ever lay a line across it. More going around builds a taller barrier wall, and a taller wall pushes the valley's floor farther out from the Sun. So a bigger, roomier circle sits at the bottom. Less going around, a shorter wall, and the floor sits in closer.
So the energy says how hard the planet rocks in the valley, and the going around says where the valley even sits and how wide it's carved. Two dials, and between them they set every orbit there is, from a tight, far circle hugging the Sun to a comet's long, lonely cigar, to a one-time flyby that never comes home.
Every orbit there is. That's what you should be seeing now. The whole family of them, circle through flyby, is one ball in one valley, with two dials on the side. The sprawl of the heavens collapsed into a single picture you read with your eyes.
Now all of this, it was mapped out long before anybody drew a single valley, wasn't it? People watched the planets crawl across the night sky for years on end and wrote the rules down by eye without any of this machinery underneath.
They did, and the one who pulled 3 clean rules out of that raw wandering was Kepler. 3 laws, and every one of them is sitting right there in the valley you just read. Let me hand them over one at a time and watch each one turn out to be an old friend. The first, the bound orbits are ellipses, with the Sun sitting at a focus.
The ellipse I've already got, that's my rocking radius drawn out in space, swinging near and far. But at a focus, what's a focus? Why not just say the Sun sits in the middle of the ellipse and be done with it?
Because it isn't in the middle, and that's the sharp little fact tucked inside the first law. An ellipse is a stretched circle, a loop that's longer one way than the other. A plane circle has a single center, dead in the middle. A stretched ellipse has, instead, 2 special points buried inside it. Call them its 2 focus points. And the Sun does not sit at the dead center of the loop. It sits at one of those 2 off-center focus points.
And why off-center? Because, oh, the valley already told me. The planet's closest distance and its farthest distance are different. The near end of the rock and the far end. So the Sun can't be dead center, or near and far would come out equal. It's shoved off toward one end.
Shoved off toward the near end. The planet comes swinging in tight past the Sun at that end and swings way out into the cold at the far end. Have you ever drawn one of these, with 2 pins and a loop of string?
Remind me how that trick goes. I think I did it in school and forgot.
Stick 2 pins in a board a little apart. Drop a loop of string around the pair of them, put a pencil inside the loop, and pull it taut. Now drag the pencil all the way round, keeping the string tight the whole time. What it traces is an ellipse, and those two pins are its two focus points sitting inside the loop.
And the sun sits on one of the pins. So one focus has the sun on it, and the other
pin is just a bare spot in space. Nothing there at all. No body, no marker, only the geometry holding the shape. The sun sits at one focus, the planet rides the traced loop, and the empty second focus sits off across the orbit, doing nothing but keeping the ellipse the shape it is. That's the first law, straight out of your breathing radius.
2 pins, 1 string, sun on one pin, nothing on the other. That I can picture. And the second law?
The second is already in hand, so I'll only name it. Equal areas. The sun to planet line sweeping out equal slices in equal time, racing near, dawdling far. It's the going around, held fixed and shown plainly across the sky. He saw the pattern in the raw motions long before anyone alive knew the reason for it. You know the reason because you know the going around is locked.
That one I feel like I earned fair and square. And the third law?
The third is about the year, how long one full lap takes. And it says, the bigger the orbit, the longer the year. A planet on a wide, roomy orbit takes longer to go once around than a planet on a tight little loop close in.
That sounds almost too obvious to be a law, though. A bigger loop is farther to travel, so of course it takes longer. Where's the catch? There's always a catch with you.
The catch is the whole point of the third law. Swell the orbit, and the year grows even faster than the orbit does. Make the orbit twice as wide, and the year doesn't merely double. It stretches out by more than double. The size and the time don't march in step. The time outruns the size.
More than double? Why more? If the loop's twice as big, I'd have guessed twice as far to walk, so twice as long, and we're square. Where does the extra slowness sneak in?
2 things gang up on the far planet at once. The wider orbit is a longer road, yes, but the planet way out there is also crawling, because out far the sun's pull is feeble, and remember, the going around has it dawdling out there anyway. So it's a longer road, and it's creeping along it. Longer path and slower pace, both together, and the two of them multiply the far planet's year out of all proportion to the mere size of its loop.
So the outermost planets aren't just a touch slower round the track, they're grinding through years that make ours look like a single afternoon, partly because the loop is so enormous, and partly because out there in the cold, they're barely moving at all.
Vast, slow, ponderous years, way out in the dark. Those are the 3 laws, dug straight out of where the planets truly stood, night after night. 3 separate rules, wrung from the raw sky by eye. And here's the thing worth carrying. Every one of them falls out of a single underlying fact, that gravity is a central, inverse square pull. Newton's gravity explains all 3 at one stroke. The ellipse, the equal areas, the ballooning years. 3 hard-won rules and one cause sitting quietly underneath them all.
So the whole solar system is a set of nested clocks then, each outer one running slower than the last, and not evenly slower, but slower and slower the further out you go.
Nested clocks, each outer ring ticking off its year more ponderously than the ring inside it, and the gap yawning wider the further out you look. The inner ones spin through many years, while a far one plods through a single lap of its own. One law, quietly sorting the whole sky into fast little inner clocks and vast, slow outer ones.
Now, something's been nagging me the whole time you've talked. You keep saying the bound orbit is an ellipse, a closed loop that comes back to the very same path every lap. But why should it come back to the same path? Why doesn't each lap land just a hair off from the last one, so it never quite retraces itself?
I'll give you the fact and skip the proof, because the proof is real work. It is the inverse square law in particular. That precise weakening with the square of the distance and no other law that makes the ellipse close up cleanly, snapping shut onto the very same loop, lap after lap after lap.
In particular, you mean some other pull wouldn't close it up?
Wouldn't. Suppose gravity faded with distance in some slightly different way, a hair steeper or a hair gentler than the square. You'd still get a valley. You'd still get a rocking radius, breathing in and out, near and far. But the loop wouldn't quite shut. Each lap, the near point and the far point, would land a little further around the sky than they did the lap before.
So the whole ellipse would slowly swing around in place, never quite closing, always creeping on.
Its long axis creeping around and around, tracing out a great slow rosette that never repeats. A flower of petals turning gradually instead of one clean closed loop. The precise inverse square is what forbids that drift and locks the loop shut. Any other central pull hands you the turning rosette. Gravity's exact square hands you the closed ellipse. And here's a whisper to leave beside it, no more than a whisper. In the real sky, the orbits aren't quite perfectly closed. Each planet feels not only the sun, but the faint tugs of all its neighbors, and those tiny extra pulls spoil the clean inverse square by a hair. So real orbits do creep round, very slowly, their loops turning by a sliver each lap, over ages.
So the shut ellipse is the ideal, one planet, one lonely sun, and the real crowded sky drifts by a whisker off it. Fine. Now here's another thread I want to pull. You keep saying the sun sits at the focus, as if the sun's a nail hammered fast in place while the planet does all the moving. Is that actually true? The sun doesn't budge at all.
Pull on that thread and it frays a little. No, strictly it isn't nailed. Here's the tidy up, and it circles back to the center of mass from the momentum night. The sun pulls the planet, but the planet pulls the sun right back, just as hard. The handshake, every push answered by its equal. So the sun does move. What's truly going on is that both of them, sun and planet together, wheel around their shared balance point, the center of mass sitting somewhere between them, the very point I told you every pair of bodies has. Neither one is nailed, both orbit the point between.
But then, why does everyone say the planet goes around the sun, if really the two of them circle a balance point in between?
Because of where that balance point falls. The center of mass leans hard toward the heavy one, and the sun is so overwhelmingly heavier than any planet that their shared point sits at or just inside the sun's own surface. So the sun does wheel around it, but only in a tiny, barely there little circle, a small wobble, because next to the vast reach of the planet's loop, that point sits practically at the sun's own center. The planet, way out and light, swings around that same point in a huge, sweeping loop.
So the fixed sun is a very good lie. Really, the two of them circle a shared point, but that point's buried so deep inside the heavy sun that the sun barely stirs while the planet does nearly all of the wheeling. Treat the sun as a nail, and you're only wrong by the width of that little wobble.
A very good lie, with the truth sitting right underneath it. It's the heavy partner approximation, and the sun is heavy enough that the wobble hardly shows. And here's the reach of this whole picture, because none of tonight was ever really about the sun and one planet in particular. The same machinery runs every orbit there is. A moon wheeling a planet, the same central pull, the same locked going around, the same valley with a circle at the floor and an ellipse rocking in it. A comet on its long, lonely journey, the same again, only a wildly stretched ellipse. Down the outer slope so far it vanishes for a human lifetime, then back in to whip once around the sun. A spacecraft we fling around a distant world to steal a little speed. The very same valley, the very same rules, worked on purpose by the people who fly it.
So every last one of them, moon, planet, comet, the craft we fling out past the planets, is the same ball rocking in the same kind of valley, turned by the same two dials.
The same valley every time. A central reaching pull. A going around it keeps locked. A well on the outside and a barrier on the inside, and a ball rocking in the trough between them. Draw that one picture, and you've drawn every orbit that ever was or ever will be.
All right, wind it all back up for me in one breath, the way you like to at the end. I walked in tonight with a small child's question, and I want to walk out holding the whole thing tied in a bow.
In one breath, then. Gravity is a central force, aimed forever at the center, fading with the square of the distance. A central force has no twist to give about the center, so it keeps one quantity locked. The going around, angular momentum, the cousin from the momentum night, paid in full at last. That locked quantity shows its face as the equal areas. The planet races when it's near the sun and dawdles when it's far. Fold the going around away and watch only the radius, and it rolls in a landscape. Gravity's well hauling it inward, the centrifugal barrier walling off the center. A valley whose floor is a circle, whose rocking is an ellipse, whose escape over the rim is a flyby. Kepler's 3 laws all drop straight out of that one valley. And the precise inverse square is the special tidiness that shuts the ellipse into a closed loop, instead of a slowly drifting flower.
And my moon, falling and missing.
Falling and missing, forever, held in the valley between the wall and the well. That's the question you carried since you were small, answered at last with a curve and a level line drawn across it.
So where do you leave me this time? Because you've got that look on your face again, the one that means there's one more door, and you're about to swing it open and walk off, leaving me squinting through it into the dark.
One more door, and then I'll let you rest. All night we've watched things go around a center. The moon around the earth, the planet around the sun, wheeling around something else, out there, far off. But a thing can also turn around itself, not circling a distant center, spinning on its own middle, in place.
A child's top, a wheel on its axle, a whole world turning on its axis, that kind of round and round.
That kind, and it hides a genuine shock inside it. And let me guess your next thought before you say it. The going around, the angular momentum, comes back for that one too.
It's exactly where I was headed. It has to come back, doesn't it? It's the going around, and a spin is nothing but going around on the spot.
It comes back, but it comes back changed, and this is the strange part. For a thing wheeling around a far center, the going around was a quantity we could get away with tracking as a plain amount, because its arrow always pointed the same way, straight out of the flat plane of the orbit, which is why the orbit stays flat. For a spinning body, that arrow is free to swing about, and that changes everything.
An arrow? And an arrow that does something odd, I take it, or you wouldn't say it with that face.
Something that looks, the first time you meet it, like a plain violation of common sense. The arrow points, and it resists, and it dodges sideways, away from the very push you give it. Lean on a spinning top, and it will not fall the way anything sensible ought to fall. It swerves off at right angles instead, and just keeps standing. Its name is the gyroscope, and it's for next time.
The going around turns from a number into an arrow that fights back. That's enough to drag me back one more night, I'll admit it. But before you go, give me the one image to carry out the door.
Take the moon. Right now, tonight, hanging over your head, it is falling, pulled straight down toward the earth every instant by the same gravity that drops an apple off a branch, never once letting up. And it never lands because it was flung sideways so long ago, so fast, that the round earth curves away beneath it just as fast as it drops. It's caught in a valley you can draw with a single line, the barrier holding it out, the well holding it in, and it rocks there, patient and endless, between the two, falling forever, missing forever.
Falling forever, missing forever. The moon that never lands and never leaves. Just a ball rocking in a valley I can draw with one line. That's the one I'm keeping. So thanks for finally answering the question I've had since I was small. And until next time, when you catch the moon out your window, riding up there as if it were hung on a string. Don't picture a string holding it up. Picture it falling. Picture the ground curving away out from under it. And ask the one question that turned it, for me, from a mystery into a machine. Not what holds it up, but how fast is it missing?